one and all. Myself Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So in the today's lecture, we are going to learn about Smith chart configuration, the continuation part of part 1 of Smith chart configuration in one of the important topic in electromagnetic waves and transmission lines. Right? So one of the foremost important one in the transmission lines as a Smith chart configuration. So it is a Smith chart is a chart which is used to represent, or it is a graphical tool used to represent reflection coefficient and standing wave ratios in a transmission lines. Right? So in order to draw the Smith chart, we require two circles called constant resistance circles and constant reactance circles. Why? Because generally there are the three different types of Smith charts are available. One is impedance Smith charts, admittance Smith charts, and immittance Smith charts. So generally or most popularly, we will use here Smith chart, impedance Smith charts as most important one. So now in order to draw that impedance Smith charts, we require general, the notation for impedance is Z, and it is given by real part as given as R and the imaginary part is represented with X. That's why it consisting of resistance and reactance. Hence, in order to draw the impedance Smith chart, we require resistance circles and reactance circles, constant resistance circles and constant reactance circles. To draw those constant resistance and reactance circles, first we need to represent it in terms of normalized input impedance, or that is represented with Z bar, which is equal to R plus JX, and reflection coefficient gamma is represented with U plus JB. So in the normalized impedance case, small r is the real part or resistive part of the normalized impedance, and X be the reactance part of the normalized impedance. Similarly for gamma, gamma is the notation for reflection coefficient. So it can be expressed here U plus JV, means where U is the notation for real part or resistive part of the, or this reflection coefficient, and V be the imaginary part of this reflection coefficient. Right? To draw that Smith chart, impedance Smith chart, we require the fundamental planes as one is impedance plane as real plane, and another one is reactance plane is related to reflection coefficient plane. As we know that this analysis, the fundamental analysis related to this Smith chart configuration, we have discussed in the previous lectures. Now continuation part of that will be considered as the fundamentals. We are going to revise in short, then we'll continue the rest of the part in this particular lecture. Then the Smith chart displays the complex reflection coefficient in polar form for a particular load impedance. As we know that reflection coefficient gamma can be expressed in terms of load impedance and the characteristic impedance of a transmission line, and it is given by here gamma equal to ZL minus Z0 by ZL plus Z0. Right? Reflection coefficient is represented with this gamma, and ZL is the notation for load impedance, and Z0 be the characteristic impedance of the transmission line. So generally this gamma be a complex number. If this gamma be the complex number, means this normalized impedance Z bar is also a complex number. Right? So Smith chart displays the complex reflection coefficient, which should be expressed in polar form, and particularly for load impedance and the characteristic impedance. Now impedance is a sum of resistance and reactance, and in general it is given by here Z is equal to R plus JX, where R be the resistive part of the impedance and X be the reactance part of the impedance. Right? So to write the this normal impedance of a transmission line, now to express this in terms of normalized impedance, we just rationalize this equation with characteristic impedance as Z0. So z by z naught is replaced by z bar, and r by z naught is replaced with small r, and x by z naught is replaced with x. Hence, it can be written as z bar equal to r plus jx. See, the normalized impedance at a location on transmission line, it can be considered fundamental one as z is equal to r plus jx. Now, from this, we are going to divide the total equation with the characteristic impedance as z naught. Then it becomes normalized impedance as z bar is equal to small r plus jx, where small r is the notation for the resistive part of this normalized impedance and x be the reactance part of the normalized impedance. So here, see, gamma equal to u plus jv and z bar is equal to r plus jx. So these considerations and all already we have discussed in the fundamental part of Smith chart configuration under part 1. Now we are discussing part 2 related, means how we are going to draw the constant resistance circles, constant reactance circles. If we combine both, how it becomes impedance Smith chart. So in case of passive loads, R is positive. Means suppose if we consider R values are to be positive. Means if in case of passive loads, R is to be considered as positive, hence R value is ranging from 0 to infinity, means resistance is lies between first quadrant of the that impedance plane, and x can be a positive or negative, and it is lies between minus infinity to plus infinity, means above that, means it lies between first and fourth quadrants, and any passive load can be represented by a point in the right half of the complex impedance plane. See, now to draw that one here, see first here, this is z bar is equal to, how we are going to write this equation, r plus jx, where r be the real part of this normalized impedance and jx be the imaginary part of the normalized impedance, and it is exist in the first quadrant of this one, means it is represented with impedance plane, right? So why? Because it is generally the notation for impedance as z, and real part is represented with r, and reactance part is, or imaginary part is represented with x. Similarly, in order to draw the complex reflection coefficient plane, see, consider real part as to be as u, and imaginary part as to be here v. Now, sometimes this gamma might be expressed along with its magnitude, means modulus of gamma, and its a phase function, means e power j theta. So, in order to represent this reflection coefficient as a complex form, then it can be given by here real part is represented on the x-axis as u, and the imaginary part is represented on the y-axis, and it is given as here j into v, right? So this is the in general impedance and complex reflection coefficient plane. Depending upon this, we have considered reflection coefficient gamma equal to u plus jv, and normalized impedance z bar is equal to r plus jx. Okay. Now, to draw the constant resistance circles, and in order to draw the constant reactance circles, first, from the part 1, we just consider here the circle equation for the constant resistance circle, and it is derived from the real part of the normalized impedance. Okay. So from that, see, constant resistance circles are given by here u minus r by r plus 1 whole square plus v minus 0 in whole square equal to 1 by r plus 1 whole square. So why it is called constant resistance circles? Means all the equation consisting of all the terms are depending upon the primary one as R, where R stands for resistance. R is the notation for the resistance. That's why constant resistance circle equation. When in general the circle equation is given by here x minus a whole square plus y minus b whole square equal to r square. So in place of a and in place of b, here we have r by r plus 1 and 0, and in place of x and y, here we'll have u and v. Okay, so u minus r by r plus 1 whole square plus v minus 0 whole square equal to 1 by r plus 1 whole square. So in place of r square, here we'll have 1 by r plus 1 whole square. Now from this, the radius r is given by 1 by r plus 1 and the center c is given by here a comma b means r by r plus 1 comma 0 was the center, right? So depending upon this, see, for constant value of r, the above equation means constant resistance a circle. Equation represents a circle in gamma plane. Gamma means reflection coefficient plane as the value of x varies with the center as r by r plus 1 comma 0 and the radius as 1 by r plus 1. So for different values of r, how the value is to be increased or decreased, depending upon that, we are going to draw constant resistance circles, right? From the center and the radius, we'll be drawing all the constant resistance circles, right? So in order to draw that, in order to find the center and this radius value, in this, we just consider, see, u minus r by r plus 1 whole square plus v minus 0 whole square equal to 1 by r plus 1 whole square as the fundamental equation and to write constant resistance circles. So for different values of r, we will get a set of circles. Means if you substitute r by 0, something u minus something whole square, v minus something whole square equal to, based upon that, we will be getting the center and the radius. Depending upon the radius and depending upon the center, we'll be drawing different types of constant resistance circles. So for different value of r, we will get a set of circles for which r remains constant on each circle. Okay, so depending upon this, see. Now first, from the constant resistance circle, center of the constant resistance circle is given by r by r plus 1 whole square comma 0. Sorry, r by r plus 1 comma 0 and the radius of the constant resistance circle is equal to 1 by r plus 1. Okay, so it is given by here u minus r by r plus 1 whole square plus v minus 0 whole square equal to 1 by r plus 1 whole square. So from this x minus a whole square plus y minus b whole square equal to r square. Now from this a comma b resembles center and r be the radius. Okay, depending upon this, center is given by r by r plus 1 comma 0 and the circle can be given as, radius is given as 1 by r plus 1. So for positive values of loads, means for positive load value, loads r is positive and hence the center lies on the positive axis of complex reflection coefficient plane, right? So complex reflection coefficient plane means there we have considered u on the x-axis and jv on the imaginary axis. So all the circles are lies based upon this u-axis only, positive u-axis only. So for different values of r and resistance and radius and the center, we are going to draw the constant resistance circles. So to draw that first, see, initial value we are assuming it starts from 0. So for r is equal to 0. So what is the center here? R by r plus 1 comma 0. Means for r is equal to 0, center is given by center c equal to 0 by 0 plus 1 comma 0 gives us 0 comma 0. And for a radius, r is equal to 1 by 0 plus 1 which is equal to 1. So depending upon this, for r equal to 0, center is at 0 comma 0 and radius equal to 1. Okay, so with the radius 1 means starting at 0, 1, 2, 3, 4 like that, the values are representing on the this u-axis. Now with the radius 1 means from the 0 to 1, we'll be drawing one circle as like this. Right? This is called unit circle with the radius as 1. Right? Next, for r is equal to 1, now keep on increasing the values of r's from 0 to 1. So first, if you substitute r by 0, center is at 0 comma 0, radius equal to 1. Now for r equal to 1, center is given by 1 by 1 plus 1 comma 0, which is equal to 1 by 2 comma 0. And radius r is equal to 1 by 1 plus 1, which is equal to 1 by 2. So with 1 by 2 means from here to here it is 1 means in between it is 1 by 2. Okay. Now from 1 by 2 to 1 by 2 and with the center as 1 by 2, now we are going to draw another circle. Okay. So like this, if you keep on increasing the values as from 0 to infinity values. Okay, see here, for r equal to 1, center is 1 by 2 comma 0 and the radius equal to 1 by 2. Now for r equal to 1, r equal to 2, center c is equal to r by r plus 1 equal to r plus 1 comma 0 means 2, if r is equal to 2, 2 by 2 plus 1 comma 0, then it is equal to 2 by 3 comma 0 is the center. Now with the radius r is equal to 1 by r plus 1, which is equal to 1 by 2 plus 1 equal to 1 by 3. With the radius 1 by 3 and consider center as 2 by 3 comma 0. Now from this you are going to draw one circle. So suppose if r values are to be increased from 0, 1, 2, 3, 4 and so on infinity. Means if r is equal to infinity, what is that center? So c equal to r by r plus 1 comma 0, which is equal to, right? So if you take r by, in the denominator if you take r as common, 1 plus 1 by r comma 0. So numerator or denominator r gets cancelled, 1 by 1 plus 1 by r comma 0 is the center. Now substitute center means r is equal to infinity, then center becomes. Suppose if r, in place of r, if you substitute infinity, 1 by 1 plus 1 by infinity, right? 1 by infinity comma 0. So something by infinity becomes 0, then 1 by 1 becomes 1 comma 0, right? So with r equal to infinity, center is at 1 comma 0 and the radius is at 0. Why it is 0 means radius formula r is equal to 1 by r plus 1. Okay, then 1 by infinity plus 1. So something by infinity becomes 0, hence r is equal to 0, right? So for r is equal to 0, center is at 0 comma 0 and the radius is at 1. For r equal to 1, center is at 1 by 2 comma 0 and the radius equal to 1 by 2. For r equal to 2, center is at 2 comma 3, 2 by 3 comma 0 and the radius equal to 1 by 3. Then if you increase the r value to the infinite range, then for r equal to infinity, center equal to 1 comma 0 and the radius equal to 0. With all these values, we are going to draw constant resistance circles, right? So as the value of r increases, the radius of the circle goes on reducing, and for r equal to r tends to infinity, the radius approaches to 0. See, if you observe like this, so if initially r is equal to 0, okay, center is at 1, and if you are keep on increasing the r values, then radius is going to reduce, right? So like this, as the value of r increases, the radius of the circle goes on reducing, and for r tends to infinity, the radius approaches to 0. See here, for r equal to infinity, radius is equal to 0. Then the center of the circle shifts towards 1 comma 0 from 0 comma 0. Okay, so this is the one we will particularly observe. Now depending upon this, see, consider the constant resistance circle equation, that is u minus r by r plus 1 whole square plus v minus 0 whole square equal to 1 by r plus 1 whole square. Now if you select for u comma v value at 1 comma 0 for the first case. So see, for infinite range, select u comma v values as 1 comma 0. Now verify if LHS is equal to RHS or not first, right? So depending upon that, we are going to draw the circles. So consider LHS. LHS means u minus r by r plus 1 whole square, u minus r by r plus 1 whole square plus v minus 0 whole square. This is the LHS part equal to. Now u means here u comma v values are to be considered as 1 comma 0. Now if you substitute u by 1 minus r by r plus 1 whole square plus b by 0 minus 0 whole square, then it becomes 1 minus r by r plus 1 whole square, which is equal to, if we take LCM of these two, then it becomes r plus 1 minus r by r plus 1 whole square. Okay, so minus r plus r gets cancelled, 1 by r plus 1 whole square. So what is this 1 by r plus 1 whole square? If you observe in the constant resistance circle, in the RHS part we'll be having 1 by r plus 1 whole square. If you consider LHS part as u minus r by r plus 1 whole square plus b minus 0 whole square, and from this if you substitute u comma value b values by 1 comma 0, then LHS part becomes RHS part. Right? 1 by r plus 1 whole square is to be obtained, and that is nothing but RHS of this constant resistance circle equation. Now, this outermost circle with center 0, 0 and the radius unity corresponds to r equal to 0. Right? Or in other words, it represents relatively loads positive on the u-axis only. Okay. Then here is the constant resistance circles. See here, if r equal to 1, this is the 1. So with the 1 and the radius as 0, we'll be drawing one circle. So here r is equal to 1 as represented as like this. Now this value r is equal to minus 1. So with the radius 1, we'll be drawing one unit circle. So highest circle radius as here r is equal to 1 in the case of constant resistance circles. Now if we keep on increasing the value of r by 1, 2, 3, 4 and 5 so on, then the radius is almost approaches to 0 only. Okay, this is the change we'll be observing as like this. R equal to 2, then r equal to 1.5, 0.5, then RL equal to 0. For different values of R resistances, then we'll be drawing different constant resistance circles. Okay, so consider this as a gamma plane only, U axis, and this is JV axis. Okay, constant reflection coefficient plane, that is real part, and here gamma R represents real part and gamma I represents imaginary part. Right? So this is the way we will draw different values of R, then constant resistance circles are to be represented on the complex reflection coefficient plane. Okay. Next, to draw the constant reactance circles. Again, consider from the imaginary part of normalized impedance plane, we will be considering this constant reactance circles as u minus 1 whole square plus v minus 1 by x whole square equal to 1 by x square. Okay, so where x be the complete equation is depending upon the x value, where x is the notation for reactance, hence the name has given as constant reactance circles. Okay, so here u minus 1 whole square plus v minus 1 by x whole square equal to 1 by x square. As we know that the circle equation x minus a whole square plus y minus b whole square equal to r square. Depending upon this, a comma b, and the center is nothing but 1 comma 1 by x, and the radius equal to 1 by x. Okay, see, for constant value of x, the above equation represents a circle in the reflection coefficient plane as the value of r varies with the center at 1 comma 1 by x and the radius is given by 1 by x. Right? So in place of r square, here we will be having 1 by x square, then from that r is equal to 1 by x. Now for different values of x, we will get a set of circles for which x remains the constant on each circle. Okay. So in order to draw constant reactance circle, we must consider all the terms are related to x only. Now, as x can be positive or negative, the centers of all constant reactance circles lies on vertical line at u equal to 1 in the complex reflection coefficient plane. So vertically means this is the way imaginary axis as JV and the real axis as U. Now all the arcs are representing towards imaginary axis, hence this will be represented as C. Now for a positive x, the center lies above the positive y axis, and the negative x values, the center lies below the positive x axis, u axis, right? So now center of this from the constant reactance circles, center of the constant reactance circle equal to 1 comma 1 by x, and radius of the constant resistance reactance circle equal to 1 by x. Now from these two, center and radius, will be drawing constant reactance circle. So before going to draw that constant reactance circles, we need to identify what is the center and radius of the different values of this x. So for x is equal to 0, first consider x values to be starting from 0. If x is equal to 0, center means center is given by here from the previous equation. What is that? Center is 1 comma 1 by x and radius is 1 by x. So center here equal to 1 comma 1 by x. So 1 comma, if you substitute x by 0, 1 by 0, then it becomes 1 comma infinity, plus or minus infinity. Why? Because where x might be means it is an imaginary one and it lies above that positive values are above that u axis and negative values are below that u axis. That's why we are considering it as plus or minus infinity, right? So whether it is x is positive or negative, we will be considering both the values. Hence, we are representing it with plus or minus positive and negative values. So center is at for x equal to 0, center equal to 1 comma plus or minus infinity, and the radius equal to infinity. Radius is given by here the formula. Radius is equal to 1 by x. Now 1 by 0 gives us infinite. Okay? So for x is equal to 0, center equal to 1 comma plus or minus infinity, and radius is given by infinity. Right? Similarly, x is equal to 0 means the impedance is purely resistive, nothing but real value, which will be represented by positive u axis in the complex reflection coefficient plane. And for x is equal to 1. So for x equal to 0, this is the way center and radius values are to be obtained. Now for x is equal to 1. For x equal to 1, center equal to 1 comma plus or minus 1 by x means 1 by 1 is given as 1. Right? So with the 1 comma 1 and 1 comma minus 1 of center, and the radius means radius is equal to, the formula is 1 by x, and in place of 1 x, if you substitute 1, radius is equal to 1. So with the radius 1 and the center 1 comma 1 and 1 comma minus 1, we are going to draw one constant reactance circles. Then if you increase the value x by 2, now for x is equal to 2, center is given as 1 comma plus or minus 1 by 2. Why? Because 1 by x is the general formula for the constant reactance circles, and here for x equal to 2, center equal to 1 comma plus or minus 1 by 2, and the radius equal to 1 by 2. Okay. Now if you keep on increasing the values from 0, 1, 2, 3 and so on infinite, how the x center and the radius values are to be changed, according to that we will be drawing constant reactance circles. So for x is equal to 3, now center equal to 1 comma plus or minus 1 by 3 and the radius equal to 1 by 3. Okay. Now for x is equal to infinity, center equal to 1 comma 0 and the radius equal. So for x equal to infinity, center is at 1 comma 1 by x. So 1 comma 1 by x means infinity, then 1 comma 0 as the center. Similarly, radius is equal to 1 by x, then 1 by infinity, then it becomes 0, right? So for x is equal to infinity, center equal to 1 comma 0 and the radius equal to 0. For all the values of x, we'll be drawing constant reactance circles with the radius, so radii and centers. Okay. Then as the value of x increases, the radius of the circle goes on reducing, and for x tends to infinity, the radius approaches to 0. As we have discussed in the previous case as constant resistance circles, here also, as the value of x increases, the radius of the circle goes on reducing, and if x tends to infinity, the radius approaches to 0. Okay, and the center of the circle shifts towards 1 comma 0 from 1 comma plus or minus infinity. Okay, so based upon this, see, now consider how the LHS and RHS paths are same. Now from this, constant reactance circles need to be drawn. So consider the equation of constant resistance circles. Now that is u minus 1 whole square plus v minus 1 by x whole square equal to 1 by x square. Now again consider for u comma v means 1 comma 0 values are considered to be as u comma v, and suppose LHS part first. LHS is equal to u minus 1 whole square plus v minus 1 by x whole square. Now in this, if you substitute u by 1 and v by 0, then 1 minus 1 whole square plus 0 minus 1 by x whole square. Okay, which is equal to 1 minus 1 square as 0 plus 0 minus means 1 by x whole square as 1 by x square, which is equal to 1 by x square. So if you observe here in the LHS and RHS part of this constant reactance circles will be equal to 1 by x square. Now from this analysis also we have got 1 by x square. This is nothing but RHS, right hand side below. So LHS is equal to RHS. Depending upon this, for we are selecting u comma v values as 1 comma 0. Okay. Depending upon this, hence all the constant resistance reactance circles passes through 1 comma 0 on complex reflection coefficient plane. Okay. So how we are going to draw the constant reactance circles? See, for the first case, if you are selecting r is equal to 0, center is at 1 comma plus or minus infinity, and radius is at infinity. Okay, radius equal to infinity. Now r equal to infinity case, center equal to 1 comma 0 and radius is equal to 0. Okay, depending upon this, first, see, if you are selecting r is equal to 0, center equal to 1 comma plus or minus infinity. So the values are to be drawn as, see, for x is equal to minus 1, see, this is the axis, x is equal to minus 1, minus jx, this one is given as minus jv, and here it will be plus jv, this is u, and this is minus u. Okay, so real part of reflection coefficient plane as represented with gamma r, or sometimes it is u axis, and this is gamma I, nothing but imaginary part of this one, and generally we are considering it as gamma equal to u plus jv, or gamma r plus j into gamma I. Okay, so depending upon that, see, x is equal to 1 means for a constant circle 1, it will be representing towards the positive axis, means above u axis, and for negative 1, minus 0, minus 1, it will be, this is the arc. So if you keep on increasing the values by x by 2, 3, 4 and so on up to infinity, then the center is almost reaches to 0 position. radius is almost equal to 0. This is the way we'll be drawing the circles as like this. This is the way we're going to draw the constant reactance circles. Dotted lines portion we just neglected. So, right? So, if we are representing, see, the circles are resembles constant resistance circles, and the arcs which are represented with dotted lines or represents the constant reactance circles, right? So, this is the way we can draw the Smith chart with the help of constant resistance circles and the constant reactance circles. Okay, so if you combine two, see, mapping of the impedance on transmission line to the Smith chart means general Smith chart is said to be impedance Smith chart. Means in this we are going to map the impedance of the transmission line on the Smith chart. Hence it is said to be impedance Smith chart, or simply we'll call it as Z charts. Right? Admittances means Y charts. Impedances means Z, Y charts. So now our complete analysis is depending upon the Z charts only. That's why it is called impedance Smith chart. So particular impedance value on the in complex impedance plane can be represented uniquely by the intersection of a constant reactance circles and the constant resistance circles in the complex reflection coefficient plane, or intersection of constant resistance circles and the constant reactance circles uniquely defines a complex load impedance in the complex reflection coefficient plane. Okay, so separately we can observe here, this is the constant resistance circles, constant resistance circles. These are all constant reactance circles. Constant resistance circles, and these are all constant reactance circles, which are can be drawn on the complex reflection coefficient plane. See, for different values of R, we'll be drawing the different circles, and different values of X reactance values, we'll be considering this arcs. See, circle intersection part means circles along with the arcs. If you combine those two, then it will be looks like Smith chart, which is having impedance parts. Z is equal to R plus Jx. Both real part and imaginary parts are exist on a single one, and we are representing it on impedances, and in general these are called impedance Smith charts. See, for different values of X, these are all dark lines are representing arcs, and if you are extending with circles, these are all represented as like this. X is equal to 1 circle and X is equal to -2. You keep on increasing the X values, -3, -4, like that. It will be reducing. At X equal to infinity case, almost its radius is equal to 0. Right? So this is the way we can draw the constant resistance circles and the constant reactance circles. Okay. Now, if we combine two on the same graph, how it will be? This is the one which are representing the Smith chart, impedance Smith chart. Then see here, all the circles are, these are all circles are representing constant, all circles are representing constant resistance circles. All arcs, these are all arcs. See, these are all constant reactance circuits. Right? So, based upon this, we'll be representing impedance, and which consisting of real and imaginary parts. Hence, the other name for this simple Smith chart is impedance Smith chart. This is the way we can configure the Smith chart with the help of constant resistance circles and the constant reactance circles. Okay. Then after that, applications of Smith charts. Where do we use this Smith chart configuration? In which applications we are going to use this one? Impedance Smith charts. So here are the some of the applications of Smith charts are given as impedance calculations on any transmission line on any load can be used as this Smith chart. Right? Now to represent all the now to calculate impedance calculations in any transmission line, we need Smith chart. Why? Because it consisting of resistance and reactance circles. Hence, in order to represent or in order to calculate the Z value, we need R and X values. Right? R is to be obtained from the constant resistance circles and X is to be obtained from constant reactance circles. And second one is admittance calculations on any transmission line on any load. So admittance is generally denoted with Y and it consisting of G plus JB, where G is the real part or conductance part of this admittance and BB the imaginary part or susceptance part of the admittance. Right? To calculate this conductance and susceptance, we need admittance. So if you use in place of impedance admittance chart, then those charts are called Y charts. So in order to calculate admittance calculations on any transmission line, we require Smith charts. And calculation of the length of a short-circuited piece of transmission line to provide a required capacitive or inductive reactance, also we need Smith charts. Okay, and followed by important one as for impedance matching purpose, we use Smith charts. Why? Because so with the help of this Smith charts, we can able to find complex reflection coefficient, that is reflection coefficient gamma as ZL minus Z0 by ZL plus Z0. Right? Now from this standing wave ratio, S is also going to find out. Then S is equal to 1 plus gamma by 1 minus gamma. Okay, where S is the notation for the standing wave ratio and in general it is given as VSWR, voltage standing wave ratio, right? And it is given by S is equal to 1 plus gamma by 1 minus gamma. Along with this reflection coefficient and standing wave ratios, we need to identify the input impedance of a lossy or lossless transmission line, that is Zn is equal to Z0 into ZL plus JZ0 tan H gamma L by Z0 plus ZL JZL tan H gamma L. Okay, or in terms of H gamma L, if you replace for it, this is for lossy one. If you want to find lossless one, then input impedance Zn is given as Z0 into ZL plus JZ0 tan beta L by Z0 plus JZL tan beta L. Right? So in order to calculate all such calculations on with the help of graphs, then we use Smith charts. Right? So with the help of this, we can able to find impedance matching also. Impedance matching means we require means in order to avoid reflections and in order to transfer maximum amount of power from source to the destination, we need this impedance matching. Means this is the case ZL is equal to Z0 or ZS. Means load impedance is equal to characteristic impedance or source impedance case, then the line is said to be perfectly terminated. And the concept is called impedance matching. Right? With the help of this impedance matching, we can achieve the avoidance of the reflections along with the maximum amount of power need to be transferred from source to the destination or from one place to the another place is possible with the help of this impedance matching. So these are all the different applications related to Smith charts. One is impedance calculations purpose and admittance calculations purpose along with the lengths of a short circuited one or open circuited one depending upon the length of that we'll be using. In different types of lengths we have considered of our transmission lines as lambda by 2, lambda by 4 and lambda by 8, half wavelength line, quarter wavelength line and eighth wavelength lines. Depending upon that we'll be considering lossy transmission line or a lossless transmission line input equation. Now from that also, so in order to calculate this also, we require Smith chart, right? Why? Because in order to calculate this one, we require load impedance ZL and the characteristic impedance. In order to calculate this reflection coefficient, load impedance and the characteristic impedance need to be performed. So in order to calculate this load and the characteristic impedance, we require this reflection coefficient gamma. So if reflection coefficient gamma is the complex one, then this standing wave ratio S is equal to 1 plus gamma by 1 minus gamma. It need to be complex one, right? So depending upon that, this reflection coefficient gamma is ranging from 0 to 1, and from this standing wave ratio S is ranging from 1 to infinity. So these calculations and all already have been analyzed in the previous lectures of this electromagnetic waves and the transmission lines. Okay, so what we have discussed in the particular lecture is continuation part of Smith chart configuration part 1. Now we have been discussed the how we are going to draw the constant resistance circles, and with the help of constant reactance circles for different values of reactance values have been drawn, then different constant reactance circles. Similarly, for different values of R, we have been drawn how we have drawn the different constant resistance circles. If you combine two, then it will be looks like exactly impedance chart. Means here is the one which is given as constant resistance circles, how these are representing in the constant complex reflection coefficient plane, and these are all the examples for constant reactance circles. See, arcs representing is in a unit circle. If you extend that one, these are all dotted lines resembles the complete circle representation of constant reactance circles. If you combine two on a single graph, it will be looks like this one. So with the help of this, we'll be calculating reflection coefficient of a transmission line gamma, the help of ZL minus Z0 by ZL plus Z0, and along with this reflection coefficient, we are also able to calculate standing wave ratio S in terms of reflection coefficient gamma as 1 plus gamma by 1 minus gamma. Okay, so from this we have and along with this Smith chart configuration, we have been discussed some of the applications related to the Smith charts also. So requirement of this Smith chart means applications of this Smith charts are in order to calculate impedance calculations, admittance calculations, or length of a lossy transmission line or lossless transmission line case. We consider different types of wavelengths calculation purpose also. We require Smith charts. Along with that, important one is for impedance matching purpose also. So why do we need impedance matching? Means to avoid reflections and in order to transfer maximum amount of power from one point to the another point, we require impedance matching, right? So these are all we have been discussed in this particular lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.